Hi, and welcome to this session where we will cover the wood beam module in Structural Engineering Library. This video will be fairly thorough. We'll try to take a look at most of the important aspects of the wood beam module, but we'll try to create a table of contents for you that will allow you to navigate to points of interest as well, so that it can be used as a reference guide in addition to an overall instructional video. So the first thing that we'll do is show you how you can add a wood beam calculation to an existing project file. I have a project file now called wood beam. I'll just click on the calculations item in the project manager and then come up and click the add button. And then in the select type of item to insert dialog, I'll come down into the beam category and choose wood beam. And that creates a wood beam calculation for me that I can start to populate. Now that we're looking at the wood beam module, I'd like to start by going through a general overview of the screen areas, the major screen areas, and explain what we're seeing here. So starting up at the top, we have a graphical representation of our beam. And this is where we'll interact with the program partially graphically and partially numerically through the use of the first couple tabs to define the physical beam that we want to analyze and design. So we'll come back to that shortly. The next major area down is this section toward the middle that has the row of tabs, and this is generally what I refer to as the input area. This is the place where you'll work with these tabs and then provide information to the program that defines the model, defines the materials, defines the support conditions, the loading, the load combinations, and so on and so forth, and sets up the model for analysis and design. So once we have our physical model created, then we will take a walk through each of these tabs and thoroughly explain what all of those are used for. Continuing down the screen, the third area that we have is what I refer to as the results panel or pane. This is the location where you're going to get information back out of the program after you've performed the analysis and design. And you can see that it's organized with a series of tabs on the vertical axis here, and then each of those has some options associated with it. And so that's where we'll complete our video today, is by walking through all of the various options that are provided for you to extract information regarding the analysis and design results. Now there's a fourth item that I'd like to point out here on the screen, and it's down at the extreme lower band on your screen, and it's what's referred to as the status bar. Right now it just says recalc complete on the left, and it indicates my build number, and for reference this is build 612926 that I'm using to produce the video. I point out the status bar because that's the location where the program will on occasion communicate with the user on important issues that are going on with the calculation. So it's essential that you keep an eye on that status bar, and every so often just check it to make sure that you're not seeing some sort of a flashing message down there that says something to the effect of, oh, for instance, no section is defined, or no load combinations are selected to run, or something like that. So good idea to get in the habit of keeping an eye on the status bar down at the extreme bottom of your screen. With that basic introduction and overview, I'd like to now focus our attention back up here to the input panel where we can define the beam that we want to analyze and design. So what I have in mind for this exercise is to create a beam that will have a 2-foot cantilever on the left, a 4-foot center span, and then a 2-foot cantilever on the right. So now we'll take a look at how we can use the tools in this little panel to create that physical model. I would point out that there's a little icon up here that shows a plus and minus symbol, and the note down here says click on the plus and minus icons to add and delete spans. Okay, so those are our plus and minus icons. Notice also that the supports form an icon when we hover over them. And this message over here on the right says click on supports to modify. And then there's also a message in the center here that says click on span to select. That'll be a little bit more obvious once we have more than just one span in view. Right now there's only a single span, so by default it's automatically the selected span. So what I'll do to add the cantilever on the left hand side is I'll come over and following these instructions I'll click on the plus and minus icon to add a new span. When I do that, the select add or delete dialog comes up, and then it has a section that allows me to add a beam and a section for some options that would apply to that new span. I can choose to use the current span length and bracing values or not. I can choose to use the current beam size and properties or deselect that one, and I can also do the same thing for the current loads that are defined on this beam. I like to come back and set all of these things individually on a span by span basis anyway, so it really doesn't matter much to me. I'll just leave these selected for the time being. And with the add beam option selected by default, I'll just click OK. Now when I do this, here is our new span, and it has adopted the span length, the section, the support conditions, and so on. The next thing that I'll do is I'll show you how you can make this into a cantilever, since that's our intent here. I'll point at the support icon and give it a click. Up comes this little pop-up menu, and then I can just come down to the free end option, and now it becomes a cantilever as opposed to a supported end. The last thing that I want to do on the left hand side of this member is I want to reduce its span length down to just 2 feet. This is the only thing that I can't actually do graphically up here on the little picture. I need to reach down to this tab named Beam Span Data and click that so that I can access a spinner control to set the span length. Now notice that in our model we have 2 beams or 2 spans defined right now, and that corresponds to the 1 and 2 selectors right here. I'd also point out that this message told us that we can click on a span to select them. So if I was to click on the right hand span, notice that it becomes highlighted in yellow. It's now the selected span, and the number 2 button appears depressed down here in the select span control. So those buttons echo the selected span up here in the graphic image. Alright, so it's span number 1 that I want to adjust the span length on, so I'll make sure that span 1 is the selected span, and then I'll come down and I'll overwrite the value of 4 with a value of 2, and then I'll just toggle the spinner arrow up and back down to register that value of 2, and now I can see that I've created a 2-foot cantilever. So things are looking good on the left hand end. Now what I'll do is the same process at the right hand end. So I'll come over to the plus and minus icon on the right hand side and give that a click. We get the same select add or delete dialog. The only thing that's different now is that we've added a new, or the program has introduced a new button called delete span to the left of support. In other words, delete the span that's to the left of the support near where I just clicked. Well, we definitely don't want to do that because that would delete our center span. So we won't choose that option. We'll leave it set to add a beam, and it knows that it'll add that beam on the right hand side of the node that I just clicked near. I'll leave all these other options set as is, and I'll just click OK. And when I do that, now I have a brand new span added to the right of that node, and it adopts the same span length, support conditions, loads if we had any assigned, and section property. So again, I'll click on the support associated with the right hand end of the new span and choose free end to make it a cantilever, and then making sure that that span is selected, number 3. I'll come down to the span length and revise it from 4 to 2. I'll toggle up and back down to register that value, and now I've created the beam that I wanted to create, which is 2-foot cantilevers at each end, and a 4-foot center span. So in preparation for the next step, I'll toggle over to the General Data tab. Now that we have our model completely constructed, we'll work our way through each of the tabs here in the Data Input panel. So starting with General Data, we have the option to enter a description. So I might call this Beam 1, for instance. The beam material category allows us to choose from among steel or concrete and wood, composite steel and concrete beams, and the None option allows us to move into the beam analysis module, general beam analysis, which doesn't perform design but just provides analysis results. Since the purpose of our video is to discuss the wood beam module, I'll leave that set to wood. And we'll come down to the next category, an important one called compression edge lateral bracing. The compression edge lateral bracing dialog or category is where we set the bracing that we want to have considered as we perform our design. It incorporates a couple of obvious options, like compression side is fully braced or completely unbraced. Those are fairly self-explanatory. And then it includes an option to say that we want to set a uniform spacing of bracing points, where the first brace starts at some distance from the left-hand end of span number 1, always using the left-hand end of span number 1 as the reference, and then continuing at so many feet on center for the remainder of the member. And then there's also an option that we will come back to called define bracing on a span-by-span basis, and here for the time being I'll just point out that the note indicates that this is something that would be handled over on the beam span data tab. That'll be the next tab we move to, so we'll finish up that discussion over there on beam span data tab. The last two items of interest here in this category are an option to use inflection points as brace points if you so choose to do that. You can select that item. And then there's also an option to force SEL to a value of 1 for all conditions if you choose to do that. Moving over to the right, we have an item called Design Method that allows us to design according to either ASD or LRFD. We'll leave ours set to ASD for this example. And then we have a category called Design Values where we're able to select the wood species and wood grade. And I'd like to point out that the way that this is done is through the wood database, which you can access from this icon right here. So I'll click that just to open up the Wood Reference Design Values database and show you that it contains many different species and grade combinations for many different size classes. And while I won't go into it in detail in this video, I would like to point out that there is a video dedicated specifically to the Wood Reference Design Values database. So if you're interested in the specifics, you can certainly get those from watching that other video. But while we're in here, I'll just come into the Douglas Fir Larch category and I'll select a number 2 from the 2 to 4 inch thick, 2 inch and wider dimension lumber category. And we'll use that for the purposes of our exercise. So I'll just come down to the select button and give that a click. Now we can see Douglas Fir Larch is populated as the selected wood species, number 2 is the selected wood grade, and all of the design values are populated based on reference to the 2005, in this case, NDS. So we have all of our design values ready to go. There are two other options that I would point out over here on the right. One of them is the option to calculate shear at the distance D from the support, so you can choose to select that or not as dictated by the conditions of your supports and your loading. And then there's also an option, if you so choose, to force the value of LE to equal 1.0 times LU. So if you want to use that one, you can simply select that option as well. So that's a thorough look at the general data tab. And now I would just like to come back over and revisit this compression edge lateral bracing for two items. The first is, I'd like to point out that this is referred to as compression edge lateral bracing, not top or bottom edge lateral bracing. So we aren't actually specifying bracing conditions for the top or the bottom specifically, but we're providing or specifying bracing conditions for any location where the member happens to go into flexural compression. So that's a subtle but important distinction that I like to point out when you're using this category. The other item that I'd like to just revisit is the fact that there's this option called Define Bracing Span by Span, which posts this note that references us to the Beam Span Data tab to define that bracing, and so that's an excellent segue into the next tab, which is called Beam Span Data. Now on the Beam Span Data tab, we were referenced to this tab by the note on the General Data tab that told us that we could come here if we chose to define bracing on a span-by-span basis. So I'd like to come directly down to the compression edge bracing for selected span category and just point out that this is where we would complete that process if that was our intent. So for instance, what we might do is select span number 1 and then say that this particular span is braced at mid-span. And then we can select span number 2 and say that perhaps this one is braced at the third points. And then we can select span number 3 and say that it's braced at perhaps the quarter points. And then as we move back through the selected spans, we can see that the program remembers the option that we chose for bracing for the selected span. Notice that there's also an option called Define Spacing, where we could choose to define a starting location and a spacing for brace points that would be considered to apply to the selected span. Again, all these options are only applicable to the selected span because we came here specifically to define bracing on a span-by-span basis. The third option here is called Define Locations, and this allows us to specify the locations of up to 3 brace points referenced from the left end of the referenced span. So we will just come back to our original plan here to say mid-span, third points, and quarter points, and that'll set us up to view some interesting information when we get down to results. With that discussion complete, I'll come back up to the top on the left-hand side here and just refresh your memory that there is a span selector, spans 1, 2, and 3 in this case because we have 3 spans defined, and that the selection here corresponds to the highlighted span shown in the graphic up above. And then closely related to that is the span length selector or indicator, and that's what we used when we initially created this beam to set the span lengths as desired. So you can use those spinners up and down to set the span length as necessary. Moving down below that, we have inputs for the maximum allowable total deflection ratio and an input for the maximum allowable live load deflection ratio, which will come into play when performing deflection checks on the member. Then we'll move over to the right hand side. We have a category called Wood Section Name, and right now this is pointing to a 4x8 member. Underneath that indicator, I just want to highlight the fact that there are 2 different buttons. There's one called Use for All Spans, but there's also a counterpart button called Use for Current Span. The important thing to understand here is that it is possible to set up different section definitions for individual spans. So if you happen to have, say, 2 2x10s that ran the full length of the member, and then had a condition where you plated the center span with some additional 2x stock, then you could potentially set that up so that you had a different definition in one span as compared to the other. For our exercise though, I'll leave it set to the use for all spans, and we'll actually stay with this 4x8 beam. It'll work well to demonstrate some results down below in a little bit, but I'd just like to show you two different ways that you can choose the section if you wanted to make a change to that wood section. First is what's called the quick list. The quick list offers a variety of different section types, so you can see general sawn lumber, southern pine sawn lumber, glue lambs, engineered wood products, and so on. And as you choose these various categories of lumber, over here on the right you see an associated list of all of the appropriate section sizes that correspond to that selected section type. So we could, for instance, come in here and say that it's a solid sawn member and it's a 3x14. And when I choose something in the quick list, notice that it populates the wood section name with that value. It also echoes that section size up here on the beam graphic. And if we glance down into the results area, it echoes that section size in the results areas as well. So that's one way that you can choose a section size for your model. The other way is to come up here and use the section database. And I will open the section database, specifically the wood section database, just to show briefly that it contains a whole variety of sections of both solid sawn and glue lamb sections. In addition, it contains a variety of engineered wood products, and then those sections are all listed down below with their corresponding section properties. I won't go into detail on all the functions in the wood section database right now because, again, I'll point out that there's a video dedicated specifically to the use of the wood section database, so if you're interested in the ins and outs of how to use it, you can certainly feel free to view that video. But what I will do while we're here is just simply come back to the 4x8 size in the general solid sawn category and choose select to show you that it now populates 4x8 as the section size in the graphic, in the wood section name, and in the results. And I would also use this as a way to issue a little caution to not be confused by the fact that you still see potentially a different section size that appears to be highlighted here in the quick list. That's simply showing you what was selected in the quick list previously, but the section to trust is the one that you see here in the wood section name and in the graphic and in the results. Now the last thing, there are actually two more things that we want to take a look at on the beam span data tab. One is the member design button, and if we use this function, what this would do is iterate through all of the section sizes of the specified or selected section type, and it would calculate results for all those sections and then sort them based on our choice of deflection or stress ratios or weight or size and so on and so forth. But it would be a quick way to get results for a lot of different sections and then select one of those sections from the list that passes all of our design criteria. The other thing that I'd like to point out is this Properties tab in the background, which represents the selected wood section name at all times. So whatever is in this wood section name input field will be represented down here in the Properties tab, and this just shows us the actual sizes, the member width and member depth. It reminds us that it comes from the solid sawn graded lumber category, and it shows us the area and the moments of inertia. It's also important to understand that it's this Properties tab where we can set some of the modifier factors that go into calculating the allowable stresses. So here is our CM value, which is the wet use factor. There's also the temperature factor, CT, that we can enter here if we need to provide something other than the default of 1. If a repetitive member factor applies, then we can select that by checking this checkbox. And if we need to apply an incising factor, that's controlled by this checkbox right here. So important to come to that Properties tab to review some additional factors other than just the general section properties associated with our selected section. Okay, so that is a thorough look at the Beam Span Data tab. What we'll do next is move on to the Span Loads tab. The Span Loads tab is the tab that we can use to apply loads to a specific span. So here is the Select Span category or control. So we identify which span we're looking to apply loads to. And then we come down and start to use the controls in this area to either add or modify an existing, add a new load or modify an existing load. Right now the table lists a line that's pre-populated for us and it's set to the none type, but by way of example, if I wanted to provide, say, a 500-pound dead load and 500-pound live load right at the free end of the cantilever, I'll show you how we can do that. I'll make sure that this load is highlighted, and then I'll click in the Select Load Type, the Point Load option. When I choose a load type, this area over here to the right reflects the input that's necessary to define the selected type of load. So notice that we have options like point loads, uniformly distributed loads, partial length uniformly distributed loads, trapezoidal loads, and then concentrated moments. So my intent is to use the point load, and what I'll do is provide a magnitude in units of kips. I'll specify a 0.5 kip dead load and a 0.5 kip live load, and then the location is always referenced from the left-hand end of the selected span. So since I want the load to be at the left-hand end, the location will be left as 0 in this case. So as soon as I click out of that 0.5 kip live load field, we notice that all of the information that we just entered up above is echoed on this highlighted line. It's a point load. It's at location of 0 or null. It has a 0.5 kip magnitude of dead load and a 0.5 kip magnitude of live load, and the same information is echoed right here. If we had additional loads, we could provide additional lines to this table by clicking Add Load or Copy Load, and then we can create different types of loads, different magnitudes, different locations, and so on. By the way, the other thing I should point out is that there is a load source here, and I could type in something like equipment, and then once I do that, that load source appears over here in the table. So that can be a convenient way to track your loads and make sure that you understand what they represent downstream. Notice that there's an Auto Add Beam Weight checkbox here. So when that's selected, the program will automatically apply the self weight of the member. And this is, although it appears on the Span Loads tab, this is actually something that would apply to the full length of the member. We can't tell it, for instance, to consider the beam self weight on some spans but not on others. It's either all or nothing. So that's the Auto Add Beam Weight option. The other option is called Auto Unbalanced Live Load Placement. This one is very powerful because what it does is instructs the program, if you select it, to look at all of the possible permutations of live load on some spans and not on other spans. So as you can imagine, that can quickly extrapolate out to be quite a few different loading conditions that need to be evaluated, especially depending upon the complexity of your loading scheme and the number of spans that you've defined in your model. So checking that option will get you some very accurate results and find the worst case loading conditions for all the structural effects that need to be evaluated, but it will also come at a bit of a computational cost in terms of time because you'll have to wait for it to process all those different load combinations, but a very powerful option nonetheless. Okay, I'm going to move to span number 2, which is the center span, and here what I'll do is use the existing defined line to just create a uniformly distributed load. I won't provide a load source description in this case, but I'm just going to assign a magnitude of, say, 0.5 kips per foot dead load and 0.5 kips per foot live load to this member so that we can see a uniformly distributed load. And I'll just jump down to the sketch here to show you very quickly that we can see the loads that we've defined so far. So this represents the load on span 2 that I just defined. And then to balance things out, I'll come over to span 3. I'll indicate that I want to create a point load, and again I'll use the same magnitude of 0.5 kip dead, 0.5 kips live, and this time I need to think about the location a little bit because it is supposed to be at the free end of this cantilever, which means that it needs to have a length of 2, so I'll enter a 2 and then just toggle to register that value. And then here we can see at location 2 there is a dead load of 0.5 kips and a live load of 0.5 kips, just as we expected. Alright, so that is a look at all of the different options that are available to us on the Span Loads tab, which is a good segue into the next tab, which is similar, called Loads All Spans. And as the note implies, the Loads All Spans tab is used to assign loads to locations that start at the left end of the beam system, so the left end of span number 1, and these loads potentially progress across more than just span 1, but could work their way out onto span 2 and span 3 and so on and so forth. So the way that you can use this tab is you come over and you can select, say, a uniformly distributed line load, in which case you would provide the tributary width and the magnitudes of those loads, or perhaps you want to define a partial length uniformly distributed load where you'd have to provide a starting distance and an ending distance, again always referenced from the left end of span number 1. This is an option to provide another partial length uniformly distributed load. So notice that you can actually have multiple loads stacked up in here with wise use of the buttons that are provided. Or you could perhaps define a linear varying load, a trapezoidal load, where you provide the start and end distance and the start and end magnitude for each of the different load cases. So let's just say, for instance, that we wanted to have something that started at the middle of or midspan of span 1 and progressed all the way over to the midspan of span 3. So the starting location would be 1 foot from the left-hand end. The ending location would be 2 plus 4 is 6 plus 1 more makes 7 feet. And then let's just provide some sort of a magnitude. We'll say that it ranges from 1 kip per foot to 2 kips per foot. And then I'll come back to that sketch so that you can see a graphical representation of that uniformly varying load that we just assigned from midspan of span 1 to midspan of span 3. So that's just an example of how that can be used. Some other options here are to use point loads, where you can define a recurring point load that starts at some location with respect to the left-hand end of span 1 and then occurs at so many feet on center thereafter with specified magnitudes, or the same kind of concept but with a concentrated moment instead of a concentrated load. Or you can do things just a little differently. You can say that you want to use concentrated loads, but now you want to define loads that will be applied to each span at the spacing indicated by the buttons down here. So for instance, you could apply point loads that occur at the center of all 3, in our example, spans, or at the third points of all 3 of our spans, or at some other defined distance from the left-hand end of the span. And again, the magnitudes can be specified as needed. The other thing that I'll point out is that we see an echo of the add beam weight as dead load and automatic unbalanced live load options here. And I just want to clarify that those are truly just an echo of the options that we see here. They aren't a different set of options. In other words, if I select the beam weight and the auto unbalanced live load placement on the span loads tab, we see that they're now selected over here on the loads all spans tab. And likewise, if I deselect them here on the loads all spans tab, we're just seeing an echo of those same controls now deselected over here on the span loads tab. So they are just two controls that happen to show up on two different tabs, and that was done because we never know that you'll definitely visit one of these tabs or the other, but we want this option to be available to you regardless of whether you might perhaps entirely skip one or the other of these tabs. Okay, so with that, that brings me to the end of the Loads All Spans tab discussion. Now, theoretically, our beam is completely loaded the way that we want it to be loaded, and that's an excellent segue into the last tab that we have for input, which is called Load Combinations. The Load Combinations tab is obviously the location where we will select and specify the load combinations that we want to have evaluated for our analysis and design. And there's a lot that's going on this tab, so we'll just work our way all the way around. Obviously, in the center of the tab, we see a representation, a numerical representation of the load combinations for the selected load combination set with their factors here. I would point out that because we chose the ASD method of design back on the General Data tab, this tab of combinations that's being displayed is referred to as the ASD or Service Combinations tab. And notice that these combinations represent service level loads as opposed to factored loads that we would use in LRFD. So it's the decision back on the General Data tab that dictates that we're seeing service level combinations for the selected load combination set. Now let's talk about the selected load combination set. What if we want to use, say, IBC 2009 load combinations? Well, no problem. We're going to use this button called Change Load Combination Set to see a pop-up list of available load combination sets on your machine. Now this can include those that are actually delivered with the program and perhaps some custom combinations or combination sets that you may have created on your own. In my case, I have some custom combinations that I've played around with a little bit, but the one that I'd like to select for now is the IBC 2009 set. So I'll just point to it and click, and now it's indicated as the load combination set that's being used. Those combinations are echoed or indicated over here in the list, and these are all of the factors associated with the combos. The next thing that I'd like to point out is that load combinations are something that need to be looked at closely. And when you read the codes and the design standards, there are some factors on some of the constituent load cases that need to be modified on occasion. What we provide is a basic set of load combinations. We expect that the user will probably have reason to want to go in there and modify certain things at certain times. For instance, maybe it's the factor on the earth pressure that needs to be adjusted based on the nature of the earth pressure load in the particular analysis that's being done. So if you had a situation where you needed to make a modification to a factor, you can do that with this little lock and unlock toggle. Right now it shows as locked, which means that I can't edit the factors, but if I toggle it, it appears as unlocked. And now I could come in here and, for instance, I could change the 1 to a 0.6 and click in another cell. And now notice that if I look at the description of that load combination, it echoes the 0.6 H that I've applied for earth pressure in that particular combination. So in that way, you could modify any of the combinations that you want, and you can do this with confidence knowing that you're not actually making a change to the IBC, or the selected load combination set. That's a database that has been read and populated into these fields. You're actually just making a change to the factors that will be used in this one particular calculation. So you won't be affecting the origin, so to speak. The other thing that I'll point out is that there's a checkbox up here. I'll relock this, by the way, just to restore that view. There's an auto minimize combinations to run. What this does is it tells the program that it can eliminate any load combinations that include snow or wind or earthquake, any of the transient loads, if there are none of those loads defined on either the span loads tab or the loads all spans tab. In other words, it just cuts out mindless work and tells the program that it doesn't have to even bother computing those kinds of combinations, because we know that they won't control if there are none of those loads defined. So that's an efficient checkbox to have selected. Continuing over to the right, I'd point out that there are some options down here to automatically create a load combination that includes both the positive seismic load and the negative seismic load. So if you check this or select this so that it shows the check mark, then wherever we have earthquake load defined, it will run not only the positive form of the earthquake load, but it'll run the same load combination with a negative value of the earthquake load. Similarly, we can do that with wind loads as well, since wind loads can go in either direction. And then we have an option up here to use the additional SDS factor on seismic loads as per the reference section of ASCE 7. So what we would do here is just enter our SDS factor, and what that will do is automatically add the small additional component of dead load to any of the load combinations that include seismic by multiplying by the appropriate factors, including the SDS factor itself. It doesn't change here in this view. You won't see the factor on dead change if we enter that option here now. But what we will see is if we go to results, we'll see those effective factors represented on the results displays. So that's a convenient option to make our look at seismic loads very thorough and technically correct. The last two items that we need to take a look at here on the Load Combinations tab are the column labeled CD, which represents the load duration factor specific to wood, and this column with the heading of Run. So starting with the CD column, what this button does, if we click it, is it automatically sets the value of CD for each load combination based on the load with the shortest duration in that combination. It's a little easier to see than to say, so I'll just click the CD button. This dialog pops up to say this will reset the CD values according to the shortest duration non-zero combination multiplier. Do you want to continue? Yes. And now we can see that it's looked at, for instance, the combination that consists entirely of just 1.0 times dead load, and it has assigned the proper CD factor for that load combination. And likewise, it's gone down through the list and it's found the shortest duration load that occurs in each of these combinations and established the CD factor correctly for each of those different load combinations. So that's a convenient way to quickly set all of those CD factors by just clicking on the CD button. And then I would mention that if we were doing an LRFD design, this button would show the Greek symbol lambda instead of CD, because the LRFD method uses a lambda modifier as opposed to CD. Finally, the Run button. There's a list of checkboxes here for each load combination so that we can selectively choose which ones we do and don't want to run. If we make some changes and then decide that we want to reselect all of them, we can click the Run button and then say mark all, or we could choose to clear all and then just select one to run, or we could even invert the selections so those that were selected are unselected and vice versa. So that is just a nice convenient tool to act on many of those checkboxes all at one time. Okay, so that is a thorough look at our load combinations tab, and that actually completes the discussion of all of the input that's required to properly define a wood beam module run. So that brings us to taking a look at our output, and we will start that by looking at the calculations tab. The first sub-tab in the calculations tab is called summary results, and when we view the summary results tab, we can see the maximum bending stress ratio, we can see the section that was used for that particular span that produced that ratio. We can see the actual bending stress and the allowable bending stress. We can see the load combination that produced this maximum bending stress ratio, the span where the maximum bending stress ratio was found to occur, and the location within that span where the maximum bending stress ratio occurred. Moving down the screen, we have a section that's dedicated to deflections. First, we report on our live load, roof live load, and snow load deflections, and we separate those into maximum downward and maximum upward deflections and their associated ratios. And then we have a section that's dedicated to total load deflections, and again separated into downward and upward extremes where we report the magnitude of the deflection and the resulting ratio. Remember that with cantilevers, the ratio is determined based on twice the cantilever length to bring it on par with a deflection ratio for a simply supported span. Moving over to the right, we have a maximum shear stress ratio reported. Notice that we report the section used to determine this maximum shear stress ratio. Now this may seem like a little bit of duplication, but just keep in mind that we did see that we had the option to define different sections on a span by span basis. So depending upon where the maximum bending stress ratio occurred and where the maximum shear stress ratio occurred, if we had defined different sections in different spans, it's possible that the section used at the critical shear stress ratio location could have been different than the section used at the location of the critical bending stress. So it is good that we see that reported for us. We see also the applied shear stress and the allowable shear stress, the load combination that was responsible for producing the maximum shear stress ratio, the span where the maximum shear stress ratio was found to occur, and the location along the span where that maximum shear stress ratio occurred. In the lower right-hand corner of the Summary Results tab, we have a section called Extreme Reactions, and it's noted to be service level reactions in units of kips. And here we have supports listed. The important thing to understand in this example is that support number 1 is a little bit of a misnomer. Perhaps it should be thought of as node number 1, because in our particular beam model, support 1 pertains to an unsupported node. So just read this as node number 1, meaning the node at the left end of span number 1, and in our case, because it's an unsupported node, obviously there are no reactions reported for it. But support number 2 and support number 3 are as we would expect. This is number 2, this is number 3, and here on a load case basis we can see the extreme reactions that occur at each of those supports. The next thing we'll do is take a look at our Maximum Combinations tab. The Maximum Combinations tab is used to present results on a load case or load combination by load combination basis. And then within an individual load combination, notice that it further breaks down the results by design segment. So for span number 1, we indicated that it was to be braced at the midspan. So that produced two design segments here, and we can see both of these segments are from span number 1. And then we said span number 2 was to be braced in a different way that produces 3 design segments. And then span number 3 was to be braced in a way that produced 4 design segments. And so that's the meaning behind these different lines that occur in this table. Each one pertains to a design segment in the member. As you read across these rows, you can see that we get a report of the applied moment and the applied shear, the final stress ratios based on moment and shear. Then we have format conversion factors and resistance factors if we're using LRFD. We can see the actual stress reported for bending and for shear, and then an echo of some of the adjustment factors that go into determining the allowable stress. We can see factors that pertain to the slenderness, and ultimately what we're working toward is our allowable flexural stress for flexural tension and flexural compression, and our allowable shear stress. So all of those are reported on I'll call them a design segment by design segment basis. Next, we'll take a look at the MVD summary, which stands for moment, shear, and deflection. The moment, shear, and deflection summary tab reports on a load combination by load combination basis. And then what it does is it indicates at small increments all along the length of the beam which span that slice fell in, what the distance was from the extreme left end of the beam system, the actual shear value that was determined to occur at that slice, and compares that with the design shear, where the difference can be the option to choose to design for shear at a distance of d from the face of the support. So sometimes the actual shear is more than the design shear. And then at that slice it reports the actual moment that was found to occur, and it indicates the unbraced length that'll be considered as it performs the design. So all of this information is on the moment, shear, and deflection summary tab on the tab called ASD Service Stress Combinations sub-tab. If we had chosen the LRFD option, then we would see the LRFD tab here, and the information would be slightly different because it would be in an LRFD format. If I move over to the Service Load Deflections tab, here what we can see are some load cases of interest for which we report deflections and deflection ratios and effective moments of inertia at increments all along the length of the beam system. The next tab that we'll take a look at is support reactions. The support reactions tab is used to simply report reactions for selected load conditions or load combinations. And again, the important thing to understand here is that support 1 is always referencing node 1, which in our particular beam model is an unsupported node. So it appears as a 0 or a blank value in the listing of reactions because there's obviously no reaction present at that location. The next thing that we'll do, now that we've looked at everything on the Calculations tab, is that we'll come down to the Sketch tab. Now, when we are on the Sketch tab, what we're seeing is a graphical representation of the beam as it's been defined and loaded. So we can see pinned supports, 4x8 sections at all segments. We can see span lengths down here at the bottom, and we can see the assigned loading that we've provided up here at the top. Next, we'll come down to the Diagram tab, and when we're on the Diagram tab, we have the option to view moments, shears, or deflections. Within any one of these, we can choose to display graphs that show all combinations superimposed on each other, or we can deselect that option and then choose a particular load combination of interest and look at the selected graph. I would just point out when you're looking at these graphs that as you change from one load condition to another, the physical size of the graph, say in the vertical direction, isn't going to change if the load magnitude changes. What happens is instead that the scale changes. So if we look at dead plus live, we see that it ranges from a value of 0 down to a value of -2. And if we go to dead only, now the scale changes so that that vertical distance represents only a magnitude from about 0 down to a -1. Okay, so that is a thorough look at all of the results that are presented down here in the results pane. In closing, what I'd like to do is just come back to the summary results tab and point out that this is the location where you'll see check marks that indicate if your design meets the code criteria and the established deflection criteria, or if for some reason you saw a red X, that would be an indication that there was a problem that needed to be studied further because it was something that was not compliant. And then the other thing that I'd like to mention is that if you come up here to this toolbar up at the top, you have the option at this point, once your calculation is complete, to preview the report that would be produced, to print the report to PDF, and you even have the ability to come into a properties button here and choose exactly which options you want to have presented in your report. I'll click close to dismiss that dialog. And that pretty much brings us to the end of everything that we wanted to look at in the wood beam module. So hopefully it's been helpful, and I would encourage you to take a look at some of the other videos relating to the other beam modules and also the related module, which would be the wood column module. Thanks very much for your time. Take care and have a great day.